Applications of the Normal Distribution, Module 4, Part 3. Our objectives are to find and interpret the area under a normal curve and to find the value of a normal random variable. Finding the area under any normal curve involves drawing a normal curve and shading the desired area, converting the x values of your variable to z-scores, then draw a standard normal curve and shade the desired area. Last, you find the area under the standard normal curve. This area is equal to the area under the normal curve drawn in Step 1. This is what we have done in previous lessons. Now we will focus on applications. It is known that the length of a certain steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45 centimeters. What is the probability that a randomly selected steel rod has a length less than 99.2 centimeters? You can see that this type of problem would be valuable in the quality control part of manufacturing. So the first thing we need to do is convert x to z. So we want the probability that our steel rod measurement, our variable x, is less than 99.2. Converting that to a z-score, we take the observed value minus the mean divided by the standard deviation and find that the z equivalent is negative 1.78. Then using the same website we've been using, we can calculate the probability that we get a z-score less than negative 1.78 is the area under the curve or to the left of negative 1.78, and that's 0.0375. And we've used technology to find that probability. The interpretation is if we randomly selected 100 steel rods, we would expect about 4 of them to be less than 99.2 centimeters. 4% is interpreted as 4 out of 100. And here's the website where the area was calculated. The combined, which is verbal plus quantitative reasoning score, on the GRE is normally distributed with a mean of 1,049 and a standard deviation of 189. The GRE is a graduate school test somewhat similar to SATs that some of you may have taken. The Department of Psychology at Columbia University in New York requires a minimum combined score of 1,200 for admission to their doctoral program. What is the percentile rank of a student who earns a combined GRE score of 1,300? So we talked about percentiles once before. What does that have to do with area under the curve? The area under the normal curve can be interpreted as a probability, as a proportion or percent, or a percentile. So here the area under the normal curve to the left of 1300 represents the percentile rank of the student. So the first step is to standardize 1300 or calculate the z-score. So we take the 1300 minus the mean of 1049 and divide by our standard deviation and find out that the z-score equivalent to a score of 1300 is 1.33. Then we calculate the area to the left of the z value of 1.33 and find out that it's 0.91 or 91 hundredths rounded to 2 decimal places. The interpretation is that the student scored at the 91st percentile, and we recall that this means the student scored as well or better than 91% of the students who took the GRE. Now we're back to steel rods. It is known that the length of a certain steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45 centimeters. Suppose the manufacturer must discard all rods that are less than 99.1 centimeters or longer than 100.9 centimeters. What the manufacturer wants to know is what proportion of those rods must be discarded. The proportion is that area under the normal curve, and we need the area to the left of 99.1 centimeters, and we need to add to that the area to the right of 100.9 centimeters. So again, the first thing we need to do when we want the area under the normal curve is to find z-scores. So the z-score for 99.1 is negative 2. The z-score for 100.9 is positive 2. Using the calculator, the area to the left of 99.1 plus the area to the right of 100.9, the calculator will do both of these at the same time if we choose the outside option and put in our standard z-score of negative 2 to positive 2. If you do this without using that software, you may have to calculate the individual tails and then add those together. But because we know the normal curve is symmetric and the left value is 2 standard deviations below the mean and the right is 2 standard deviations above the mean, it shouldn't be a surprise that both of those areas came out to be the same. The proportion of rods that must be discarded is 0.0456. This means if the company manufactured 1,000 rods, they would expect to discard about 46 of them. You wouldn't have to go with 1,000. You could also say if they manufactured 100 rods, they would discard about 5 out of every 100 rods, because 0.0456 rounds to 0.05, which is the fraction 5 out of 100. Now let's find the value of a normal random variable. So now we're going to reverse the process. If they give us the probability, can we go back and find the value of the variable that generates that probability? The procedure for finding the value of a normal random variable corresponding to a specific proportion, probability, or percentile, and all of these are interpreted as the area under the curve, is to first draw a normal curve and shade the area corresponding to the appropriate proportion, probability, or percentile. Then it says to use a table, but we're not going to do that, to find the z-score that corresponds to the shaded area. And then once you find the z-score, you have a formula for changing a z-score back into an x value, back into a data value. Use the website we've been using to do step 1 and 2. So we're not going to use any tables. We're going to use this website or a calculator if you're using a calculator. Then find the original data value x by multiplying the z from the website calculation by the standard deviation. That's what's going on here. The z-score times the standard deviation, and then you add the mean back to that, and that turns it back into an x value. So turning back to the GRE data, with the mean of 1,049 and standard deviation of 189, what is the score of a student whose percentile rank is at the 85th percentile? So this time they're giving you the percentile and asking you what did that student have to score to get in the 85th percentile. The z-score that corresponds to the 85th percentile using the software is a z-score such that the area under the standard normal curve to the left is 0.85. So we put our area here, and note that that's the correctly shaded part, put below, and we get our z-score of 1.0364. or rounded to 1.04. Now, step 3 in this process is to use the formula and convert that back to x. So the formula says that I can get x if I take the mean and add the z-score 1.04 I just found times the standard deviation of 189, and that will convert it back to an x. So my mean of 1,049 plus 1.04, my z, times the standard deviation for this data of 189 tells me that the student had to score a 1246 to land in the 85th percentile. So a student who scored in the 85th percentile had a combined GRE score of 1,246. It is known that the length of a steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45 centimeters, so our same rod data. Suppose the manufacturer wants to accept 90% of all rods manufactured. Determine the length of rods that make up the middle 90% of all the rods manufactured. So I need to know the middle 90%, which leaves 10% on each tail. So you have 5% on this tail and 5% on this tail. Converting those to a decimal, the area would be 0.05, and I need to know what measurement corresponds to those areas. There are 2 ways to do this on the website. You could use the 90%, 0.90, between So I put the 0.90 and use between here. Or you can interpret it as you are discarding 10% on each side. So you can put the 10% area in and say you want the z-score that gives you an outside area of 10%. And notice either way, we get the same two z values, negative 1.6449 and positive 1.6449. So using those z values, we'll put those into our formula and find out that the first x value that corresponds to the z of negative 1.645 is 99.26 centimeters. And using the second z-score in that formula, we take the mean of 100 plus 1.645 times our standard deviation of 0.45 and find out the other measurement on the high end is 100.74 centimeters. So the interpretation is that the lengths of steel rods that make up the middle 90% of all steel rods manufactured would have lengths between 99.26 centimeters and 100.74 centimeters. This is an egg incubation problem. The mean incubation time of fertilized chicken eggs kept at 100.5 degrees Fahrenheit in a steel air incubator is 21 days. Suppose that the incubation times are approximately normally distributed with a standard deviation of 1 day. What is the probability that a randomly selected fertilized chicken egg hatches in less than 100 days? What's the probability that a randomly selected fertilized chicken egg takes over 22 days to hatch? And what's the probability that a randomly selected fertilized chicken egg hatches between 19 and 21 days? Would it be unusual for an egg to hatch in less than 18 days, and why? So the first thing you need to do is change all of that data to z-scores, because we can't do anything with probabilities until we standardize the information. So the probability that a randomly selected fertilized chicken egg hatches in less than 20 days, the z-score for 20 would be the data value 20 minus the mean of 21 divided by the standard deviation of 1, and that gives us a z-score of negative 1. What's the probability that it takes over 22 days? So the z-score for 22 days would be a positive 1, and the z-score for 19 days would be a negative 2, and the z-score for 18 days would be a negative 3. Notice that these all came out to be z-scores that aren't fractional. So we could use the empirical rule to do this instead of the website. Then we calculate the areas. So the probability that a randomly fertilized egg hatches in less than 20 days would be the probability that x is less than 20, but we converted that 20 to a z-score of negative 1, so the probability that x is less than negative 1 is 0.1587, or about 0.16, which if we put that as a percent would be 16%. This means that out of every 100 eggs, about 16 of them are going to hatch in less than 20 days. And again, notice that we could have worked this problem using the empirical rule. What's the probability that a randomly selected fertilized chicken egg takes over 22 days to hatch? So our z-score for 22 was positive 1, so the probability that z is greater than 1 using the website, we find that area to be 0.1587, or about 16%. And this means that out of every 100 eggs, about 16 of them will take longer than 22 days to hatch. Note that we could have used the symmetry of the graph in our answer from the last problem to answer this part without actually doing the area calculation. The area below a z of negative 1 is equal to the area above a z of negative 1 on the standard normal curve. And we could also have done that with the empirical rule. Part C, what's the probability that a randomly selected fertilized chicken egg hatches between 19 and 21 days? Since 21 is the mean, its z is 0, but if you plug it into the formula, it will calculate out to be 0 if you don't just recognize that. And using our website, the probability that a randomly selected egg takes between 19 and 21 days to hatch, so that would be between a z of negative 2 and 0, is 0.4773. In other words, about 47% of every 100 eggs will hatch between 19 and 21 days. Would it be unusual for an egg to hatch in less than 18 days, and why? So we found the z-value for 18 to be at -3, and if we calculate the probability, that leads us to answer yes, because 18 days is 3 standard deviations below the mean. The probability that an egg would hatch in less than 18 days is just 0.0014. That means about 1 egg in 1,000 would hatch in 18 days or less. Typically, an event that has a likelihood of less than 5% is going to be considered unusual. You could see if you ran a big egg production farm, it might be interesting to know this information. Now take the Module 4 Part 3 Assessment of Learning. The password is apps.